Share screen. So everybody has the lecture notes with you guys?
Which one should we be looking at?
Note 8. Just a moment. Okay, for the moment, let me just share. Not so homework 6 and 7, not completely, maybe a part of homework 6, but okay, so can you see my screen now?
Yes, we can see it.
Okay, so we are in page, so we did up to this point. So we defined for a n cross n matrix, we have this polynomial. So if you take the determinant of A minus lambda of I, what you get is a polynomial. And we define the characteristic polynomial to be this particular polynomial for a matrix. So this is the point where we stopped. At least that's what Bob told me, that he did up to this point. But let me recall what, just give me a second, let's see if I can do that. Yeah, questions? Okay, good. Now you can see a page, white page.
Yes.
Great. Okay, so now I feel empowered. Let's say I have a page to write. I'm not very good at that, but anyway. Okay, so we have a so what are eigenvalues? So we have a matrix A. So this is, let's say, a n cross n matrix. Now, an eigenvalue eigenvector equation is the following. So you have A times a vector X gives you a lambda times the same vector. So this lambda, this is called the sorry, not vector. This is called the eigenvalue for A, and the vector X is the eigenvector. Right, so this is an eigenvalue and eigenvector, they come up a lot in, let's say, practical examples in rotational motion or any kind of dynamics, or if you study computer science, if you assign a coordinate to anything, then eigenvalues and eigenvectors will come up. Can I see questions? Questions? The point is, if I share the screen, I cannot see your questions on chat. So feel free to ask by unmuting, I guess. Let's see. Okay, I can see the questions. Eigen 2 or eigen 3? No, eigen 1. Eigen 1, page 14. Which chapter in the book is this? It is chapter 6 of the textbook. Okay, should we be already able to do homeworks? Maybe part of homework 6, not homework 7. Yes, which is not a question. Which homeworks will be tested on midterm 2? Let me check. Homework 6 for sure. Actually, homework 6 you can do completely right now. Then homework 7 and I would say homework 4 and 5. But I mean, the second test is basically another homework. So it's not really a test because I'll post the test on eCampus so you can see it there and solve it. And we have to figure out a way as to how you can get back the answers to me. So it's not really a test. I will give you maybe a couple of days to finish off the answers instead of a test. So you can finish it off in 2 days, let's say. And if you really want to get a test, just sit for an hour and 15 minutes, find the time, sit for an hour and 15 minutes and finish it off.
You know what day you're going to be releasing that?
31st, August 31st. Sorry, March 31st. Yeah.
So a week from today?
A week from today, yes.
Okay.
Yeah. Okay. What? Oh, everybody can hear. So I see 3 people, or a couple of people saying I can't hear anything. So everybody can hear me? I can hear, okay. Yes, okay. Can hear, yes, okay. Okay, for the moment, let's assume that everybody can hear. Okay, so let's carry on. So we have this eigenvalue, eigenvector, sorry. Oops. Okay, so we have this eigenvalue and eigenvector equation. Okay, so what does an eigenvalue and eigenvector does to a matrix? So this this matrix A, this acts on this vector, right? So think of it geometrically. So what an eigenvector does or eigenvalue does is it doesn't change the orientation. So suppose you have in R2 something like this. So if you act by a matrix on this vector, then it will keep the same direction or it might reverse the direction, but it cannot go somewhere like this. That's not allowed. and it changes the length by lambda. So the lambda is the magnitude of the change of length of the vector x, and it keeps the same direction, or it just reverses the direction. So it cannot orient itself any other way. Okay, so that's what eigenvalue and eigenvector are. Let's see. Now, how do you find an eigenvalue and eigenvector? So given a matrix A, let's see. So what does AX equals lambda of x means? It means that if you bring this lambda of x on the left, so what you have is the following. Agree? Now, collect A minus, so you can rewrite this in the following way. A minus in, sorry, lambda times in right? So agree with me up to this point. Now, oh, come on. Okay, so what does it mean? So A minus lambda in, it's a matrix, right? And you have, so remember that, so recall that this x should be non-zero. So what it means is that you have a solution for this system of equations, right? So A minus lambda in times x equals 0. So you have a non-zero solution. So what it means is that it means two things. Number one is that, okay, so the determinant of A minus lambda in should be 0. Right, because it has a non-zero solution. And number two is that if you take the null space of A minus lambda of I, this gives the eigenvectors. Okay, so questions? Any questions so far? Let me write. Okay.
You said eigenvectors plural, like there can be more than one for a
There
certain
can be
a given equation.
infinitely many eigenvectors, exactly. There can be infinitely many eigenvectors for a given eigenvalue. Actually, we'll see. So, I mean, you see that this null space, A minus lambda in, gives all the eigenvectors for a given eigenvalue. And in general, you know that this is a vector space, right? Null space of a matrix, it's a vector space or a subspace of a vector space. So there are infinitely many vectors. So all such vectors will be an eigenvector for this given eigenvalue lambda. So given an eigenvalue, there are infinitely many eigenvectors. Okay, let's carry on. Oops, not here. So basically, given a matrix, these are the two things we will see. So we will solve these two equations. So we will solve number one to find the eigenvalues and number two to find the eigenvectors. Okay. Now, what is this? So what is this determinant. If you think of it, so this, for a n cross n matrix, it gives you something like this. So A11 minus lambda A12 up to A1n, AN1, ANN minus lambda. Okay, so this is the determinant. So it only changes on the diagonals. Only changes on the diagonals. So what we get is exactly that in the lecture note. So if you go to page 14 of your lecture note, so this is eigen 1. So go to page 14, there is this theorem which says that, so this is the theorem, that this determinant A minus lambda I, this is given by something like this. So you have -1 to the n, lambda to the n, plus some C1, lambda to the n minus 1, plus up to this constant Cn. So this is the theorem. Okay, so this is a polynomial in lambda. So it has n roots. So it can have n roots, but n complex roots. So roots may not be real. That's the point. For example, if this determinant is given by something like lambda square plus 1, so then it has all complex roots. Okay, let's see. Let's do this example step by step. So page 15. Okay. Two, one, one, two. Okay, so this is a very concrete 2 cross 2 matrix. So what is the, so we call, let's go back a bit. Why is it, okay. So this equation that the determinant of A minus lambda in equals 0, we call this equation a characteristic equation. And finding this particular, where is it? This null space of A minus lambda in, we call it the null or the eigenspace of the eigenvalue lambda. Okay, let's see. So far, so good. No questions so far. Everybody can hear me? Okay, good. Let's see. So what about this matrix? So what is the characteristic equation? So let's call it P lambda. So this is A minus lambda I2. So we want the roots. So this equals 0. So what is this? This is 2 minus 2 minus lambda, 1, 1, and 2 minus lambda. So this is 0. Okay. So this is the, okay. And I mean, you have solved plenty of determinants. So this is -1 equals 0. So the eigenvalues, so these are the eigenvalues. So eigenvalues are given by the roots. So eigenvalues are lambda 1 equals 1 and lambda 2 equals 3. Okay, so these are the two eigenvalues. Now to find the eigenvectors. Okay, so now eigenvectors. So what do we need? We need to find, so let's give this the following name. So E of 1. So this will be the null space of A minus 1 times I2. Okay, let's get back to some pages. Let's give this a name. So this will be called E of lambda. So the eigenspace corresponding to lambda. Okay, so we want to find E of 1. So null space of A minus lambda I2. So what is A minus lambda I2? Rather, A minus 1 times I2. So this is 2, 1, 1, 2 minus 1, 0, 0, 1. So this is 1, 1, 0, 1. Okay, so we want to find the null space, which is not so difficult. So we want to find the null space of this particular matrix. Okay, but it's almost immediate in the sense, let's see. So what does it mean? 1, 1, 0, 1. 0, 0. So this equals, let's see, x plus y equals 0 and y equals 0, right? So this is what it means. Okay. Just a moment. Wrong. Oh, maybe there is a, oh, it's 2, 1, 1, 2, sorry. Yeah, this is what. What's going on? Just a moment. Okay. So this should be 1. Sorry, I somehow cannot rub this out. Okay, so that was the mistake. Let's see. Okay, so this should be 1. So now what we have, we basically have the same equation. So we have, let's see if this works or not. What's going on? Anyway, so let's just, for the moment, something is not working. So we have the same equation. So x plus y equals 0 for both. So what does it mean? It means that a general solution xy is given by, so you replace x by minus y and y. So this is y times minus 1 and 1. Okay, so what it means is the following. What's going on? Sorry, guys. I mean, I will be an expert in a couple of classes, maybe. This is something even I'm sort of learning as I go on. Okay, so what it means is that the eigenspace of 1, so this is given by null space of A minus I2 is same as the span of, sorry, this vector. Yeah, it's 4-1, maybe hit undo. Yeah, but I mean, I have a like virtual eraser which should work. I don't know why it's not working. Yeah, so it's 1 everywhere, and that's what we get. So now all of you agree with the answer. So this is the eigenspace for 1. Similarly, so this is something I leave for you. Similarly, eigenspace for 3. So this is the null space of A minus 3I2. And if you check, so this will be span in exactly similar way. So span of this vector. Okay. So any questions about the example? Is it clear what's going on? I mean, the technique is not hard. You have this these two things to do. So you have number 1, so solve this equation, and number 2, you find the eigenspace by finding the null space. So you know what to do, just that you have to relate it to what you are now doing, basically. Okay, so another example. And this is not completely computational. So suppose you have A in the following form, half okay. So this is our matrix. Find find, okay, now I'm in trouble. Now it's working. Who knows what happened? Find an eigenvalue and an eigenvector for A. The thing with this is that you can either solve it using the technique that you know. So you solve this matrix A minus the determinant of A minus lambda I equals 0, and then get some eigenvalues and eigenvectors. Yeah, so for the previous question, no, E3 doesn't have the same span. E3 span is given by 1, 1 on both the components, and for eigenvalue 1, it's minus 1, 1. Yeah. So they're different. And if you notice, they are actually, so if you take the dot products of the two eigenvectors, it will be 0. So it means that one is perpendicular to the other. Okay. Okay, so find an eigenvalue.
Will that always be true? That when you have two eigenvalues for a given vector, that they'll be perpendicular?
No. In this case, it's orthogonal. In this case, they are perpendicular, but there would be situations where when they're not. But something which is true is the following. So suppose you have two different eigenvalues. So lambda 1 and lambda 2. And lambda 1 and lambda 2 are different. Like in this case, you have 1 and 3. Then the eigenvector corresponding to one eigenvalue and the eigenvector corresponding to the other, they will be linearly independent. So although they are not perpendicular, they won't depend on each other. That's something we will see later. Okay, so what about this, this particular problem? Can you think of a way to solve this without going into the actual equation? You see that the rows and the columns are somewhat special for this matrix, right? So they add up to 1. So the rows add up to 1, the columns add up to 1. So what you can do, so let's see. Since I cannot see your faces, it's kind of a sad situation. I mean, teaching a class online is something completely different. Anyway, this rows adding up to 1 should ring a bell a little bit at least. So what happens if we multiply, let's see, multiply A with this particular vector? So if you do the row operation, so this is half, half, half and half times 1, 1. Okay. So now recall the matrix multiplication that you know. So this is half plus half. So this is 1. Then half plus half, it's 1. Okay. So what does this mean? So what is an eigenvalue and an eigenvector? So recall, so if I write it here, so this is an eigenvalue eigenvector equation, right? So what is an eigenvalue and an eigenvector here? You can write on chat if you want. Exactly. So 1 is an eigenvalue. Yes. And what about the eigenvector? Exactly. Yeah. The eigenvector is given by 1, 1. So eigenvalue is 1 and corresponding eigenvector is 1. Okay, so this is something which is special for this particular problem. I mean, you cannot use this technique everywhere. This type of matrices, they are called Markov matrices, and they appear in something called stochastic analysis. So this is something sort of a stochastically balanced matrix. Okay, let's carry on. Let's see. More examples.
Oh.
Yep.
Um.
Yep. Question? I can hear you. Or you can type. Or we can carry on. Okay, so let's do this one. So now A is a 3x3 matrix. So 1, 1 minus 1, 1, 1 and 1, and 0, 0, 2. Then same idea. So you have this characteristic equation, A minus lambda I3 equals 0. So this is the eigenvalue, or this is the characteristic polynomial which will give you the eigenvalue. Okay. Now, if you solve this equation, so this will give me, so this will give the following equation. So 1 minus lambda square. So I am not going into the details, times 2 minus lambda. So this is the determinant, and that should be equal to 0. Okay, so it means let's see, that the eigenvalues are given by the following. So the eigenvalues are lambda 1 equals 2, of course, from this particular root. And then 1 minus lambda square minus 1 equals 0 means, well, lambda minus 1 square equals 1. Okay. Which means, let's see, lambda 2 equals 2 and lambda 3 equals 0. Okay, so these are my 3 eigenvalues. And if you notice, lambda 1 and lambda 2 have the same value. So we say that the eigenvalue 2 is repeated twice and eigenvalue 0 is repeated once. Okay, so I didn't solve the determinant, and I mean, it's there in the lecture note. So if you want to verify the details. And now the eigenvectors. So eigenvectors, so E of 2. So this is the null space of A minus 2 I3, right? Now, if you write out A minus 2 I3, it's going to be the following matrix: minus 1, 1, and minus 1, 1, minus 1, and 1. And the third column is completely 0. Okay. And now we can solve this. So we want the following. We want the solution for the system 1 minus 1, 1. Okay, so this will give us the eigenvectors. Okay, and you can see that row 1 and row 2, they differ in sign. So if you add row 1 to row 2, what you get is that the second row becomes all zeros, right? So then you can transfer this matrix to the following. So this is 1, minus 1, 1, minus 1, 0, 0, 0, and 0, 0, 0. Okay, agree? So I just added row 1 to row 2. So these are the, the old row operation techniques that we're using. So what does it mean? It means that minus x plus y minus z equals 0. Okay, so this is the only equation that we have to solve this system. If you change it a little bit, so what we get is that x equals y minus z. Right, so minus x plus y minus z is 0, means x is equal to x is equal to y minus z. Then what does a general solution look like? So x, y, z, you can replace x by y minus z, y and z. Okay, so this equals y times 1, 1, 0 plus z times minus 1, 0, and 1. Okay, so remember how we wrote down things as a linear span. So this is what we're doing. Okay, so what does it mean? It means that the eigenspace for E2, the eigenspace for 2, which was the null space of A minus 2I2, I3 rather. So this is given by span of these two vectors. So 1, 1, 0 and minus 1, 0, 1. Okay, so this is the answer for 2. And similarly for E of 0, so this is simply null space of A, right? Because it's A minus 0 times I3. So it's simply null space of A. And if you check, you will get this to be span of, let's see, minus 1, 1, and 0. Okay. Now I leave this for you to check. So check that if you collect these three vectors, so the one eigenvector for 0, and let's put it here. So you have these two eigenvectors for 2, and this one for the minus 1, 1, 0 for 0. So if you collect them, so 1, 1, 0, minus 1, 0, 1, and minus 1, 1, 0. So check that this forms a basis for R3 in this case. Okay, so this I leave for you to do. And I guess this is a good point to end, although officially this class is an hour and 15 minutes, but online, I think it's better to keep it like this. So we have what, 50 minutes class. And so what I want to do is for you to read the lecture notes, and classes would be more or less like 50 minutes, and office hours, we can discuss the rest. So this is where we will end, and we will begin on Thursday from page 22. 22 of note 8, I guess, is it? Yeah, note 8. Okay, so that's all for this section, and I will be back. So if anyone wants to join me later, so I'll be back at 3:30 College Station time. Or yeah, so office hours would be not just for questions. So you read the lecture notes and we can discuss the lecture notes on office hours. I mean, it's from 10 to 12, but we can, I mean, as you notice, it's just a time which we need to slot, but we can go on basically for maybe 15 or 20 or half an hour more. So the office hours would be sort of like an intermediate between asking questions and sort of discussing things. Okay, so that's all for the moment, and I'll come back at 3:30. Okay, bye for now, and have a nice day and stay safe. That's the most important thing. Okay, bye.